Hi, I'm Ben-Yaakov. This presentation is entitled Skin and Proximity Effect, an Intuitive Explanation of Dowell's Loss Model. When it comes to the design of an inductors or a transformer, here is an inductor with a air gap and transformer, primary and secondary. There's always the question is how to minimize conduction losses. Of course, there's also the problem of core losses, but we are now concentrating on conduction losses, that is the losses due to the resistance of the wires, and how to choose the wires and the type of the wire that will bring about the minimum losses. So this is the subject matter of this presentation. In 1966, Dowell published a pivotal paper entitled Effects of Eddy Currents in Transformer Windings, which since then has been like a beacon in this area. Although there have been many other models and improvements and extensions, still in the region or the envelope of operation that usually you are designing a magnetic component, the Dowell's model seems to be working pretty good. In the paper, Dowell developed a number of expressions, and here's one of them for the ratio of so-called RAC and RDC. We're going to talk about it. But as it turned out, to say the least, these are not very user-friendly, which might explain why workers in the field they are not that familiar with these expressions and they are not using it that much. So the objective of this presentation is really to present in an intuitive way what is the skin effect and the proximity effect versus skin effect, what are the consequences of the proximity effect, and how to choose the wire size and type for minimum loss or optimal design. When it comes to losses due to low frequency current, then the derivation is very simple. You take the RDC, this is the low frequency resistance, times R squared, and this will be the power dissipation. For that, you need to know the total length of the winding, here it is LT, the specific resistivity, and the cross-section area of the wire. Of course, you have to do it for the primary and the secondary, which are shown here. This is a cross-section of, say, of this transformer. When it comes to AC, or high frequency in particular, the situation is much more complex. Here I'm showing a slab of a conductor, say copper block, through which a flux, magnetic flux is penetrating. Here is the magnetic flux density, and when it comes to a certain area enclosed in, say, this circular path, we are talking about a flux, magnetic flux, and according to Faraday's law, the change in flux induces a voltage n times the phi dt, and if the number of turns, here we have one turn, and if this path has a resistance R, then there's going to be a current here, which is V over R. So this is a phenomenon due to the fact that an AC, high frequency, magnetic flux is penetrating a conductor. And I'm showing here one frequency, like B sub 0 sine omega t for the magnetic flux density, but in reality, the waveform might include higher harmonics too, that you'll have eventually take into account. Now, if we have a wire through which a current is flowing, then this current is also inducing a magnetic flux, and consequently, there are going to be eddy currents in the wire itself. And notice that at the outskirt here, the eddy current is actually being added to the main current here and here, while in the middle, it's canceling it to a certain extent. So if we look at the cross-section, what we are going to see at high frequency, that the current is concentrated around the rim here, while in the middle, there is no current. So in fact, you are losing copper, you might say, you are losing area, and consequently, the resistance to the AC component, this high frequency component, is larger than the DC for which the current is passing throughout this cross-section area. Now, same phenomena or similar phenomena is happening when you have two wires or more, that in one there is a current, maybe in the other there is also current, and this current of this wire is inducing a magnetic flux into this one and vice versa. And consequently, again, here we see that in this particular case, this current, this eddy current, is added to the outer border here, while it's being subtracted from the main current at the middle. And consequently, if we look at the cross section, we're going to see that the current is concentrated here at the two edges, and this is the proximity effect. Again, here RAC will be smaller than RDC, of course, and depending on the frequency, we're going to lose quite a bit of an area here, which makes the resistance high, and therefore the losses will be high at high frequency. So now let's have a look at the transformer, and which has a primary and a secondary, wound like this. And I'm going to sort of tilt it 90 degrees for convenience and have a look at it here. This is a window, one of the windows here. I'm looking at this one with the primary and secondary. And we understand that if there is a current in the primary and secondary, then it's going to be a magnetic field, H. And according to Ampere's law, the circular integral of H that is going through a closed path is equal to the ampere turn, N times I. Also, we know that H is B over mu, total mu, which is this relative permeability and vacuum permeability. And therefore, for a given B, if mu R is high, then H will be small. So if I'm going through a path here, circular path here, well, it's not circular, but through a closed path here, I have two regions. One within the ferrite, this is the ferrite, the body, the core of the transformer. H is small. However, in the window, inside the window, the H should be higher because then we have only mu sub 0, which is air, approximately. And I'm here inserting only one layer, okay? So I have a certain magnetic field, which I'll find here. Here, it's very small, I can sort of neglect it. Now, since the H, the magnetic field outside is small, then I can calculate the magnetic field inside as M, which is the number of wires per layer, M here, and B is the length here. So the magnetic field is M times I, this is ampere turns. This is ampere turns divided by the length here, okay? And of course, I'm neglecting this length here because here H is very small. So here I have an expression for the H here. Now, if I'm choosing another path, which is up to the two layers, the magnetic field will be higher because I'm now encircling a much higher ampere turns, twice in this case. So typically what I'm going to see is that at the beginning, the magnetic field is 0. Then as I'm passing through the first layer, it's going up. Second layer is going even higher. And then since the secondary current is in opposite direction, in transformer, the primary and secondary, in fact, current cancel each other. Then in this case, as I encircle the third row, it'll go down H, magnetic field, and then it'll go down farther. Okay, so this will be a profile of the magnetic field within this window. Okay, and in the original paper, Dowell actually showed a number of cross sections here just to explain the concept. And that is, here I have the primary, and this is the secondary, primary, secondary. And we see here that the magnetic field is going up, and then it's going down. Here we have an interleaved case in which we have primary, secondary, primary, secondary. So we're going up and then down, up and down. And here it's also interleaved, but it's not symmetrical, and this is why the field is not symmetrical. So this will be the field within this body, within the window where the wires are. Now, due to this field, as we understand now, these will induce eddy currents, and this eddy current will change the way the current is passing through these conductors, through the wires, and consequently our AC will be larger at high frequency. And in fact, in the paper, Dowell developed this relationship, which in this case is talking about the ratio between RAC and RDC, and it is a function of the height, that is the height of the layer, the number of layers, and some other parameters that I'm not going into, because we have today calculators that will calculate this for us very quickly without us going into the fine details here. And here in this website, which is very nice, it's Encyclopedia Magnetica, they have a calculator. So you put in the diameter, you put in the frequency, the material of the wire, temperature, and number of layers. Porosity is the packing, that is, if it is a round wire, maybe a square wire. And then it'll calculate this proximity factor, which is RAC over RDC. And in this particular case, for these particular numbers, it is 17.6, which is a lot. That is, the RAC is 70 times, almost 17 times larger than RDC. Now, there is another parameter here, Q. I'm going to talk about it in a second. And then we have also the skin depth, which is calculated from these parameters, and in particular, the frequency, of course, the type of material, etc. And we'll see this also in a while. So once you have this calculator, really you can very easily find what will be this RAC over RDC for a given layer. And you can now plot the sort of summarize the result in a plot like this. And in this plot, what we see here, this is RAC over RDC. This is Q factor, which is the diameter, actually it's the height of the layer, to be more precise, divided by the skin depth. And here I'm showing the expression for the skin depth. It's pi f, the frequency, mu sub r. This is the relative permeability, mu sub 0, and then sigma is the specific conductivity of the material. So it's material dependent, both from the electrical and magnetic characteristic. And this is delta, this is this thickness here, which if you have a single wire and you have a current, then the current will be concentrated in this band. Now, also shown here is the skin effect by itself. That is, if somehow you manage to cancel out the proximity effect, there are some ways to sort of lower its effect. Then you are left with the skin effect, and here it is. And as you can see, the effect is much lower than the proximity effect, so that in most applications, proximity effect or losses due proximity are much higher than the losses due to the skin effect, especially at the higher harmonics, high frequency. Now here is sort of a zoomed view of this same chart. Again, this is the ratio between RAC and RDC. Here are the layers, 1, 2, 3, etc., up to 10. This is the Q factor, D over delta. Here's 0.5. The meaning of 0.5 is a case in which you have bifilar winding. That is, you have primary, secondary. So they are sort of canceling each other to a large extent. And this is why, relative to all the other the RAC is much lower than the other. So this is really actually the best thing to go. But of course, we have problems here of insulation, first of all, between primary and secondary. There's also problem of capacitance between the wires. So in many cases, you would avoid this and rather have layers rather than a bifilar in which you sort of wind it with the two wires together here. And again, this is the expression for delta. It can be approximated for copper, it's, well, for a given temperature, of course, etc. It is 72 over F, where F is in hertz, 72 is the number, and the delta is millimeters. So for a given frequency, you can calculate very quickly what is the skin depth. So if I have now a wire which is exposed to other wires in, let's say, a transformer at high frequency, I have the current being concentrated here at the two sides here. Now, if I reduce the diameter of the wire, it'll look like this. If I reduce it farther, it'll look like this. In this case, Q, which is D over delta, is getting smaller and smaller. So in this case, we are going this way. It's going smaller and smaller. And RAC over RDC is also going to be smaller and smaller. So it's sort of improving, but you have to take into account that although this ratio is becoming smaller, RDC by itself is becoming larger because you're going to a smaller cross-section area. So you can take this into account. But the point is that normally, well, except for some exceptions, you are not gaining anything by having an oversized diameter of a wire because the current is not occupying all the cross-section area. So let's do an exercise here. Suppose I have a transformer in which I have, in this, say it's the primary, two layers with large cross-section area wires, and I'm going to replace them by the same number of wires, that is, same number of turns here, but of smaller diameter. So the question is, due to the proximity effect, are the losses here going to be lower or higher than the losses here? It's not a trivial question, and as we'll see, the answer is counterintuitive. So let's have a look how we can derive or how can we infer what is really going on in this case. To do that, I've plotted here a line which is y is equal to x to the power of 2, x squared. X is here, y is here. Now, the reason for doing that is because if I'm reducing the size of a wire, you're reducing the diameter, the resistance will change as a function of 1 over d squared, because the area is a function of d squared, and the larger the area, the smaller rd, or vice versa, the smaller the area, the larger is r, and the functionality here is d squared to this squared. So I can therefore say that the slope of this curve is exhibiting this relationship. That is, if I move from one point to another, RDC1 to RDC2, this is equal to D2, that is the diameter of the wire in the second case, over D1 squared. And this is because of this relationship here. So this line helps me to see what happens if I'm changing the diameter of the line in terms of RDC. So let me start off with examining this case, which is kind of an eye-opener, I think, from which we can learn a lot. I have moved here this line toward the 10th layer of a transformer. So I have a transformer with 10 layers, and I've moved the line here, and this is the 10th layer. This is RAC over RDC, and this line helps us to examine this relationship, okay? So I'm starting with a Q of 2, Q is D over delta, and then I go to 0.5. So the ratio is 4. So I'm going to reduce the diameter of the wire or the height of the layer fourfold. Consequently, the change in resistance will be according to this line, and this difference now is, of course, 4 squared, 16, okay? Because this function is to the power of 2, this sort of helps me to understand what's going on. So now let's have a look for these two Qs, 2 and 0.5, what is the RAC over RDC for the 10th layer? Well, here it is 100, and here it is like 1.6, 1.7. So this ratio of moving from here to here is 60. So I've gained resistance RDC by 16, while RAC over RDC went down by 60. Okay, so the ratio is 3.75. RAC over RDC went down by 60, while RDC by itself changed by 16. So the ratio is 3.75. So what does it mean? It means that RAC for the larger wire was 1. This is sort of a normalized value. And when I reduced the wire, the cross section of the wire, to 0.25, fourfold, RDC went up by 16, but I gained by RAC over RDC 60. So consequently, RAC will be 0.26. So this means that for the 10th layer, RAC of a thinner wire will be much lower than RAC of this bigger wire. This is kind of counterintuitive. You would have thought that perhaps RAC to RDC is changing, but if you have a thick wire, then RAC by itself will be low. Well, it turns out that that's not the case. Now, here I'm not taking into account the lower layers. I'm just talking about this upper layer number 10. So let's have a look now at a more interesting case, which is perhaps more practical, and that is the following. Suppose you have 2 layers and you have used large diameter wires. Now I'm going to reduce the diameter such that I'll have only 1 layer rather than the 2 layers. And the question is again, will the power dissipation be higher or lower when you compare these two together? I have here 2 layers, 4 wires. I have here 1 layer with 8 wires, so ampere turn is the same current is passing. So which one is dissipating more power? So let me use this same concept that I've shown earlier, these 2 lines which are showing this square function. And in this case, I'm going to change Q from 4 to 2. That is going to change the diameter twofold. Why twofold? Because if you change it twofold, then you can put, instead of 4 wires, you can put 8, okay? Because now the diameter here is half this one. So I'm start with 4, I'm going to 2. Now, as far as here is this sort of a table summarizing what is happening. I've started here, and in here, I have layer number 1, which is this one. I have about 4, RAC to RDC is 4. I'm assuming that D is 1 and RDC is 1, just normalizing it. And for the second layer, I'm here, and this is about 12, okay, RAC over RDC. And this is when I have these two layers with the larger wire. Now I move to Q equals to 2. So the diameter is half. Since the diameter is half, I can compress these two layers into one layer. So now I'm talking about this layer only, no matter what this one, because I have only one layer now. And our AC over our DC is about 2, and this would be for all the wires, okay? This is like two sections of the same layer, one original and one actually transferred from the second layer, reduced the diameter by 2, but the RDC resistance will be going up by 4. And the end result is that while in the first case I had a total power loss of 16, this is again normalized unit, as it turns out, for this particular example, this would be exactly the same for the one layer. So in this case, if you have these two layers and you reduce by half the diameter, you end up with this one layer, much less copper. The power dissipation of these two will be the same in this particular case. Again, this seems to be a bit counterintuitive. You would have thought that indeed you lose here in terms of copper, but the absolute RAC should be here lower than perhaps here. Well, in this case, so what can be done? The best thing, of course, is to use very thin wire. But if you use a thin wire, you cannot carry the current that you need. So therefore, you need a bundle of thin wires, which is called the Bliss wire. And it's one way. This is the best thing. And they are twisted here for other reasons that I'm not going into. And here it shows here, these are strands which are made into one bundle, and then everything is twisted again. And this is important not only for the first harmonic, but remember, in a converter, the current is not sinusoidal. Well, just in resonant converters, and even in resonant converters, rarely you have a sinusoidal one frequency component of a current. Usually there are some higher harmonics. So you have to take into account that for the higher harmonics, you are moving here because the delta is becoming smaller. That is the skin effect, which is the functional frequency in the denominator, a square of the frequency, is as the frequency increases, you are moving here and the losses become larger. So one has to take into account that if you're even running a converter, say at 100 kilohertz, that you'll have to actually accommodate losses of higher and higher harmonics. So this is why you need a very thin wire. And this is one way to do it. These, of course, have to be insulated one from the other. Otherwise, it's like a chunk of copper if everything is conducting. So these are to be insulated. And it is not cheap, but this is what you need for high frequency operation. Another way to go is to use a tape, and it has to be thin. This is the D here. So you can then wind the primary and secondary, only one of them, with this tape conductor. Let's take an example of the type of wire that you actually need. So suppose you have a 10-layer case, and I'm looking now at the 10th layer, and I like the losses to be low as much as I can in order to reduce the total conduction losses. So I like to move to somewhere here, okay? And we are talking about a Q of 0.25, okay? So if I have 10 layers, let's say 100 kilohertz, then the skin depth will be 72 square root of 10 to the fifth, which is 0.22 millimeter. So now to get Q 0.25, I have to multiply this by 0.25, which brings me to a wire diameter of 0.055. Now, assuming that I'll allow a current density of, say, 5 amp per millimeter square, which is kind of a conventional, acceptable, good number in terms of losses. Of course, so you can make it a higher current, but then the losses will be higher, or lower current, and then, of course, the conduction losses will be lower. But this is like a good number. And then it turns out that this strand can carry 10 milliamp. This implies that for 1 amp, you need 100 strands. And for 10 amps, it'll be 1,000. And if it is like more than that, then proportionally it's going higher and higher. Now notice that these are very thin strands, okay? And in fact, it is highly recommended to actually use a thinner wire, again, because of the higher harmonics. I've assumed that everything is 100 kilohertz, but say if it's a PWM, this is certainly incorrect because you have, say, if it is an inductor, say, you have a triangular waveform, and therefore you have an appreciable amount of higher harmonic. Another way to go is to use flat or planar magnetics, in which the geometry of the ferrite is a bit different. In this case, the window for winding is relatively small, while the cross-section area of the ferrite is much larger. So you are trading, you might say, ferrite or core area by winding area. So you have a smaller area for the winding. The height is lower. So this is kind of very compatible with the requirement of low proximity losses. Okay, you have fewer layers, and of course you can make them thin. And here is an example. This is just one example. It's one company. There are a number of companies who are making these transformers. And what we see here is the ferrites, and then the layers or the windings, primary and secondary, actually are different here. In the primary is on a printed circuit board, it's the green one here, while the secondary actually is a plate. It's called so-called lead frame. It's a copper plate. So this is for a heavy current on the secondary. It has only two windings, here and here, while the primary, there are a number of traces here. This is primary, and this is primary, and this is primary. And so you have an N to 1 or N to 2, N will be the number of the traces here. Now, you need insulation, and these are the red colored plates here. And then there are some also heavier insulation between primary and secondary, so as to avoid breakdown if the voltage is expected to be high. So this will be then the shape of the ferrite, and then all is compressed into something of this nature. So this is another way to go to reduce proximity losses. Now I'm coming to the case of inductors. The theory is basically the same, except that we have now some more complication here. And that is that if we have an air gap, then around the gap, we're going to have fringes. And consequently, these are causing high magnetic field on the wires adjacent to the gap. So here, we are going to suffer from a lot of RAC resistance. That is, the resistance will go up very high because of the very strong magnetic field here. So one way to go is to actually remove the wires from the gap, that is to put the wires away from the gap. It's a little bit complicated, but it can be done. Another way is to use a distributed gap, that is material like iron powder, which have a low mu sub r, relative permeability, and by this you will reduce quite a bit the flux, which is sort of moving from the ferromagnetic material into the window. So this is another way to go. And here I'm showing another approach for inductors. which is becoming now more and more popular. And this is the helical winding. Okay, here's the winding itself. That's the wire. It's a flat wire, but it's put here horizontally here, shown here. And the point is that this structure is actually one layer only. So this is actually one layer with the wires or conductors like pillars here, okay? And here they are. And therefore, you don't have a number of layers. And as we have seen from the Dowell model, the problem is layers. And if you have one layer, you're in pretty good shape. Obviously, this is not exactly the same plot here for this particular helical winding, but we can understand the concept of having this helical type of a winding, which is again one layer. And of course, the expressions are different. And also, the fringes here are less harmful because they are only affecting part of the conductor. Okay, it's not like a bottleneck uh, increasing the resistance of a single pin conductor, which is in this area. This is the cross section of the inductor, and we are harming only part of it. So this is a very good way to go for inductors that are based on ferrite with air gap. So let me summarize some of the observations that we've been through in this presentation. We see that the proximity effect is responsible for the main high-frequency conduction loss. See that one layer is the best. Bifilar winding is also very useful, but of course there is a problem of should be insulation and capacitance problem. Then flat magnetics is very compatible with low losses due to proximity effect. Distributed gap also will reduce the inductor losses. And then we see that helical winding is really effective when you have an air gap. Bliss wire or thin tape is really a must at high frequency. There's no way around it. At very high frequency, you need either very fine mixed wire or a thin, very thin tape. Now I'm talking about frequencies of hundreds of kilohertz, not to mention 1 megahertz. Well, 1 megahertz is becoming a very tough problem, okay, because of the very high frequency and the very thin skin depth. And also we have to take into account that in many applications, the current is non-sinusoidal, so you have to consider the fact that there are higher harmonics. Also, I think that Dowell and other models are only approximation. There are many issues that are not handled. For example, the edge effect that is at the end of the layer, it's behaving differently. The geometry affected. So these are first order approximation. And today, what has to be done if you have a design is really to do a finite element analysis. And this is actually the ultimate tool to estimate conduction losses for a given structure. You can do it 2 dimension or better off 3 dimension and get a pretty good estimate of the losses. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much. This for a given delta, that is for a given frequency, material,